Let's go to LeetCode 2022. Word search 2. So this question it gives us a multiple byte board of charts and this string words. Return all words on the board and say that each word must be constructed from the letters of sequential adjacent cells, where adjacent cells are horizontal or vertical neighboring. So comparing to word search 1, and word search 1, it gives us a string of words and let us to see whether these words appears in the board. We just return false. But now we need to return a list of string. That is, for this list of words, we need to find all of them which will appear, which can be constructed from the letter of sequential adjacent cells. So intuitively, what we think about is that we do like the word search 1, but the thing that we just false string with my word and word and we do word search 1, right? And this return true and false, right? If it is true, then add to the result. The problem for this kind of research, this kind of approach is that if we have, for example, length words, for each word, we have a DFS that will be the m multiplied by n and the power 4 time complexity, and it will have length words multiplied by length words operations. So it will the time complexity will not be that good. That means that because every time we search a word, we'll go through all of the cells of the board, right? And so we have some repeat operations. That, for example, for the word 1, right, we will go through everything, and word 2, we'll go through this as well, right? So we're thinking about can we save this part for each step that for the word when we can create something like the prefix and it have a list of words, right? This a string of words. That's, for example, if we have if we have for example, apple America, right? So everything we start at A, right? We can find from this prefix dictionary, because we can use the map, right? We have A something, right? And also, for example, applause, right? Applause. So we can create something like a prefix sum map, right? Which have the key as a string, and the value will be list of the word which is coming from this word set. Then every time we go through one step from the board, we just try to iterate the prefix one by one, right? So that one iteration is board from the I to M in the row from 0 to m in a column and 0 to n, and this step by step. And the other is that we try to iterate for this kind of cell, what kind of prefix it can compose. Then if this kind of list of strings, for example, is empty, we can terminate those kind of paths earlier, right? So that if we have prefix sum as key and also a list of string as a value, then we can save on this part about such words. And to use a map as prefix sum and list of words as a value, we can introduce because it we can introduce another data structure called trie, which is doing the same thing as prefix sum with the map with prefix sum, and the list value is list of words. Use trie, it do the same thing like this, but it save much more spaces. To write trie it is that we have an empty node first, and for each trie node, we define something called trie node. It have 26 child, depends on if it is lowercase English character, 26 child, and for each child node, that is each child is also a child node. And so, for example, for each channel, it may also have several 26 children. So if there is so it forms a tree called trie tree. So it have two. We can have some kind of operation. For example, insert a word to the chart. It is just for example, there is a word. For example, it is the word W, right? So it will go to the W path and go to this kind of node. And if there is O, right, go to O path and go to this node. And then there's R, and there is D, right? So when iterate goes when this path finish, right? We go to a node. We can save this kind of, for example, this word into this node. When we add those kind of string to this data structure, when we try to search this kind of string, for example, we want to search the word whether it exists, right? We just the same thing is that we're trying to go through the path W, right? And then trying to go to see O, right? Trying to see whether this path exists, and OR, and then go to D, right? And then go to this node. If we have, for example, we use a flag is word, right? Is word. If it is true, then let's say this word, we find it from this data structure. If we don't use a flag, we can just use a string at the beginning to set as none, right? Set as none, and when we insert finished, we set the node for this this string property to be this word. So let's begin to write code for this. As we discussed, so if we use prefix sum map or a chart structure. Every time we iterate the cell, we one step, right, on the board. On the other index, for example, that is on the channel, right? On the channel or prefix sum, right? We just go one step on the chart to the next node. So that we don't need to for every word we do a DFS, that is multiplication. So let's begin to write code. Firstly, we need to define. Of course, if someone is interested, we can he can use prefix sum catch map to list the string to write this question as well. But let's use char their structure. Let's call class called channel. And for this channel, it has this listed as children. Children. This is a constructor, and we'll see this children equals the new char node 26. Yeah. We can add some other properties. For example, we can have a Boolean this word, right? For this one, because we only store those kind of words, every word in the word is distinct. When we only store that word, so we can only store that word when we finish inserting, right? So we can have a parameter called string word, right? And only when we insert the word, when it's finished, we'll set this word to be the one we insert. So the default word was not. Let's write some corner cases. Let's list the string result equals new array list. And we'll say if this board equals to null or board but length equals to null, not equals to 0, or board 0 dot length is 0, or board dot length is 0. We just return result. So let's create a char tree, right? The char tree, and we have a root equals new main. And we are going to write a function private we call void insert. And first we need to do some preparations from this word array and insert every word to the char tree. So we can have char node as my root and string word. We're going to have a char parent from the root, and for each character, the word each array. let's say, equal current of children. C goes to A equals to none, right? Then we'll have current of children equals U no, in the current equals current children. C minus A. So only after we insert this word, we can set current dot word equals word. So we have to first thing is that we do some preparations. That is for each string word in with words. I'm going to insert root word. Um, now let's write. Still we have int m equals board of length m board 0 dot length. But for int rows equals to 0, row smaller than n, row plus plus. And for int column equals to 0, column smaller than n, column plus plus, right? So the same thing, pretty much like what we do in word search one. We can have a Boolean related array called new Boolean and and we have related row column equal to and related row column false, right? So we want to write a DFS. DFS, of course, we need to have a port into it. And we need to have the current row column. And related array. Also, we need to have the trie map, the chart or tribe data structure, right? So we have the root, and we need a char node which iterate on the char tree, and this node at the beginning is also actually the root. Then result. In the end, we just return result. So let's write the DFS function for this. That is UI DFS. So we are saying it's a char board, right? Board in the current row, current column, and a Boolean relative. And the char tree, right? Char node root and char node current and the list of string result. let's get this character called row column. Well, say mm, so when we iterate to this row and column, um, we'll say if this child node children, right? Node that current the children c minus a. That is for this character in the child tree, if this one equals to none, then we need to return right. We need to terminate. Then let's move to its child. What's your current? It's current by children c minus a. And we'll say if current dot word is not none, right? Then we'll add this to our result. Result add word. Also, we'll say if the current but not be talking about right? Because we this one does not this one okay we already have this right, so just add this to result. The thing that we already, that means this word in this kind of words list exists, right? In this case, we don't want to search anymore. So we can set this current of the word to be null until we find such word. Then the things that we are trying to iterate to the four directions of this board, right? So we need to have the direction array, right? Int the array static final int the row equals 1 0 minus 1 0. Array static final int the column equals 0 1 0 minus 1. And we iterate the four directions in the board. So it was for int a equals to 0 with smaller than 4 with plus plus. We have int new row equals to row plus b row a, and the int new column is column by b column a. So let's try to see if it is in bound or not. If it's not in bound, we continue. the new row smaller than zero or mm, n equals 4 dot length and for zero dot length. If a new row smaller than zero or new row greater or equal to n or new column smaller than zero or new column greater or equal to n or if we have verified this new row new column, then we just continue. Then we set the new row, new column equals to 2. And the DFS, right? After DFS, so we backtrack new row, new column, that's to false. DFS, that is support. New row, new column, repeat that. And the child tree. And then now current already goes to its child, right? So we can still have current and have result. Let's try to see whether it's coming. When doing the chart sheet, we can optimize the solutions. We can add another property, for example, for count, right? That means when we insert for each path, right? Every node will have a count property. For example, have count here, right? So if we insert, for example, apple, for this node, the count will +1. A p node, this will also +1, right? That means this prefix a and ap, in the end, it will appear this count times. So if we add this attribute, And when we find our word, we can, for this word, we can do this count from the root, write something to write a count minus to get these counts decrease, right? And when we search, if we find out no, this count is already to 0, then we don't need to search the chart anymore. We don't. In this case, if we add counts attributes, it can we can terminate or do that DFS trimming, get the things faster. So let's add this attribute. At the beginning, this count equals to 0. So when we insert, right, we just need to have a current dot count plus plus. That means for this kind of chart tree, right? For example, we have a count. This prefix, it will have these counts words in the word list. So when we find a word, right? If we find a word, we need to remove this word from the chart tree, right? We need to write a help function called void. We call remove child no root thing word. Because for this word, it's already been inserted, right? So for those kind of word, if we find it, we remove it. Those kind of paths will always exist. So this kind of logic we don't need anymore, right? So we just need to have current node equals root, and for char c equals word to char. And I have C equals to C that children. Sorry. Current equals current without children. C minus A. And I will have current count minus, right? So if we find a word, right, we just write remove this kind of root from root to current word. And now and now we'll say if current count equals to 0, right? We can terminate. Current. Well, sorry, we should when we should do this. Because the root the count is always 0. We should write when we goes to its chart if the current or current the trailing is a dot count equal to 0, then we terminate. Let's 全新。We should put this one here. Instead, we should put because we already set this one as none, right? So we should the order matters here. So let's submit our. So let's see if we have a count variable in every channel, the efficiency improves a lot. For this question, so to discuss the time complexity, right? We'll see for we are going to iterate the board, which is n multiplied by n. For each board, it has 4 directions, so that will have power 4, right? And for each direction, we try to see compare with the child node child tree, right? The child, if there are n word, the child it is just save the space for us, but it's similar to a prefix sum hash map. So we still need to compare for each step. We need to compare those kind of lengths in chart tree, right? So it pretty much will be n multiplied by n, and part powerful and also multiplied by the word length with my L. Okay.